Hey guys, welcome back for the very last time. This is the last time I'll be able to open a video by saying welcome back. So it's making me sad. This is the final video. This is it. This is the end. These are the final exams, the final gym exams. And it's finally the end of the year. What a year we've had, right? So I imagine a lot of you guys are excited, but very bittersweet way, right? Happy that it's almost over, but also just very tired. I'm getting tired too, honestly. So I'm very looking forward to the break that's coming up. But anyways, congrats making it this far. We're so close to the end, right? Just gotta tie in a little bit. So we're gonna go ahead and do the gym finals. There's two of them, right? Normally I do three. I did two because I'm just getting tired. First one, very doable, I think. If you can do this, you probably can do the exam. Second one has a little more thinking to it, but very, very doable. Again, just a little more thinking. And the second one's a bit more even on material. I based the first exam off of last quarter's exam before there was any talk about how the final was going to be formatted, or at least before I knew anything. So I made this one really 25, 26 heavy. So I apologize, but two is a lot more. I mean, yes, the scaffolds are 25, 26, but they all involve reactions from all over the quarter. So nothing to worry about. And as always, we can always talk about more reactions, right? You can always add more reactions, especially with, once we're traveling back in time to some of these older reactions where we can kind of substitute things and see what happens. Stuff like that. Okay, cool. So we'll go ahead and we'll get into the midterms. Now, normally I do a review, but for the sake of time, I want to finish this within an hour and a half. And also just the fact that there's not a lot of new material. We can get through all the material we need to as we talk about questions. So I'm not too stressed about, knowing or not knowing something or not having said something. We'll go through every question, any trick or anything we need to know, we can go ahead and get it out of the way with that question. So I imagine this first midterm will probably take us about an hour and 15, just because we'll probably have a lot of content talk. And then we'll kind of breeze through this one as we go through old material and don't have to stop as often. Okay, cool. All right, so let's get right into it. First question here is going to be heterocyclopentadiene, right? It's a pyrrole. We're doing a BR2, like an EAS type reaction. So here's the deal with the heterocyclopentadienes. Okay, so generally speaking, these guys all follow this kind of formula where it's a 5-guard ring, 2 pi bonds, and some heteroatom with a lone pair. Number of lone pairs don't matter as long as it has at least one, right? The heteroatom lone pair conjugates to the ring system. Okay? So two things that kind of tells us, right? One is that, okay, we have conjugate electrons. So these are pi electrons. And if we count the number of pi electrons, right, with, including these lone pairs, right, we have 6 pi electrons. So this is an aromatic system. And also, right, if this lone pair is being counted, it's aromatic. So a lot of qualities in that, right? One is that it's very acidic, very non-basic, this lone pair. You should never be using this lone pair to pick up a proton, okay? Never, ever, ever pick up a proton with that lone pair. It is the least basic of them, right? It's down there with the nitrile in terms of basicity, okay? So an aromatic lone pair, don't use it as a base, right? It's not its job. Actually, we even call these kinds of lone pairs pyrrole type lone pairs. Okay, so we're going to come back to this, but I'll say pyrrole N. If you ever hear me say pyrrole N, I'm talking about a nitrogen whose lone pair conjugates in resonance that affords aromaticity. Okay? Another thing is that if these electrons are resonating into the ring, right, this ring is relatively electron rich, right? It's pi excessive. So there's a lot of electrons in it, right? And so generally pi excessive, a lot of electron juice. These guys are very, very juiced up to do nucleophilic reactions. So what I mean is that the ring itself is a nucleophile, or does EAS. So adding in an electrophile, very, very easy thing to do on these heterocyclopentadienes. Okay. Now, generally, where do things go on a heterocyclopentadiene? Usually you'll get additions onto the C2 positions first. Okay, so technically it's just like C2, and this would be like C5, right? But with nothing on them, like if I guess if I put this here, then it's like a, well, let me put it here. That way this is a C2, that's a C5, right? You want things to go there first before you go anywhere else. The general common cited reason for this is that C2 additions have more resonance forms. Now, I don't want to draw them out. I'll just say it. And that's not a bad thing to think. A lot of a lot of reasons for why heterocyclic reactions work the way they do is what I like to call coping reasons or coping mechanisms, because really this is like very advanced homolumo things. We just try to boil these down into very quick and easy rule of thumbs to make it easier to predict before you pay a computational guy in your department to like figure out where exactly something will go based on the homolumo maps. But yeah, so generally, on a heterocyclopentadiene, if you have to put something somewhere, put it on the C2 and the C5 first. And then if you have to, you can go and put on C3, C4. Okay, but we can see here, right, we have these two positions open, or sorry, one of these two positions open. We have the C5 position open. And so BR can add very happily into that position. Okay, now obviously if I wanted to put another electrophile in here, right, it could either go here or here. Very likely it'll go here. Think about the deactivation, right, between these two deactivating groups, right? Carbonyl is way more deactivating, probably deactivates this pi bond very, very well. It's also, if you think about this position, it's like meta, right? This position's like meta to the carbonyl. So it's the most nucleophilic position relative to the carbonyl, right? It's also ortho to this bromine, which is an orthopair director. So kind of has a doubling effect there, right? Cool. So electrophile would probably definitely go here, but you wouldn't be required to know that. It's just a thing to think about. Okay. Now, here's a really good question, right? These guys very, very primed for EAS, but what about NAS, right? Could I potentially add, let's say, like a nucleophile to a pyrrole? And so obviously, if I just have a naked pyrrole, right, nothing else on it, this is not going to work, right? I mean, again, pi electrons, high density of electrons, nucleophile is usually also a source of electrons. I mean, these are just two things going to, ram their heads into each other. It's not going to work at all. So let's kind of go back and think about, well, okay, a benzene ring. Let's say that I want to do an NAS on a benzene ring. What are the things that I could do? Well, benzene is not very electron rich, so you can also just brute force this with the benzyne, right? You could go through benzyne, kind of brute force this. You obviously can't do that here because, again, very, very electron rich, so this is just not going to work. But we could also, right, add like in a withdrawing group, and the withdrawing group acts as sort of an electron sink. So the electrons from the nucleophile have somewhere to go. Right, they're going into some, sink that can stabilize them while they're there. So if I actually look at this setup here, right, this is actually the perfect setup for doing NAS on a heterocyclopentadiene because we have an EWG that is in conjugation with the position that has a leaving group. And so if I add a nucleophile in, right, yeah, it's kind of like that whole ortho-para thing, right? We have that ketone or that EWG that's ortho. Sorry, it's para to the BR. You can imagine this will also work if it were here too, right? Because that would just be ortho. Okay? But we can add a nucleophile into this position. Electrons can sink into the carbonyl, right? And the nucleophile can be accepted very readily. Okay. Obviously now all that remains is kicking off the X group, right? Just like that. And so we have now successfully added in a nucleophile. Yep. So yes, generally 5-membered rings should only really be doing EAS reactions, but if you wanted to, you could do an NAS. It's not impossible. Okay. We'll come back to this with pyridines and thinking about, okay, pyridines, those guys are good at NAS, but they're bad at EAS. So what are some workarounds that we could do, right? Things that make this reactions better or easier. Yep, cool. All right. But just for now, we'll call it there on the heterocyclopentadiene stuff. Obviously, and we just want to talk about this in chunks so we can get through problems, right? We're not just stuck on this for the rest of the night. Okay, cool. But for this one, right, we're just going to go ahead and go on the C5 position, right? Let's say that we started from here, right? Let's say we started from here and we wanted to know, where the next electrophile would go. Again, very likely it would, I mean, it would go for sure C3, C4 position, and much more likely to go next to like an orthopair director, right? Something that can direct electrons, or something, some kind of cue, like for the fact that this would be an EWG that kind of takes away electrons from here. Okay. Oh, I guess the one thing we can ask ourselves is, how can we make this, right? So if I wanted to ask like an extra question, how can I make that? That's actually very simple, right? This is a acylated benzene ring, or sorry, acylated aromatic ring. That's just a Friedel-Crafts. So I could just do a Friedel-Crafts here, right? And I can get to here. So you could actually even build this SNAR-capable pyrrole if you wanted to from scratch. Okay, cool. All right, so we'll just move on from here. But that's the little first taste on pyrroles. Okay, we have an aldehyde and, oh, damn, shoot. I made a mistake. Okay, this is a typo. I'm pretty sure this is a typo. So we have an aldehyde here, and hopefully you guys see instantly is that you see the CN and you see the ammonia. This is meant to be a Strecker synthesis, right? Where the aldehyde essentially is replaced by CN and NH3 plus, right? Because we're an acid. This, if you hydrolyze it, right? So if you hydrolyze this, will lead to an amino acid. Right, like this, which is what I meant for this to be, but I forgot that. So it should have been this. I apologize. That's my bad. Happened. So the correct answer for this question would actually be this. But more correctly, right? It should just be that you do a hydrolysis into the amino acid. So what's really cool about this reaction visually, to think about it, is that you're just replacing the aldehyde with sort of the amino acid like V, if that makes sense. Like you can kind of draw all this again. Doesn't matter what's attached to the aldehyde, so long as it's an aldehyde, and you just kind of get rid of that. You just replace it with a V that has your acid and your amine, and there you go. That's your amino acid. So very cool trick. This also means that retrosynthetically, if you were thinking of using Strecker, right, you just have to replace this V here with an aldehyde to get back to a reasonable intermediate, a less complex intermediate, and think about how can I make aldehydes, right? Thinking about old ways of making aldehydes, maybe one way is like dipole, right? That's just like from an ester or something for sure. For example, right? PCC of an alcohol, right? So things to just think about, right? Get those brain juices flowing for the final. Cool. All right, that's all we'll call for Strecker now. It's not much more to talk about this. Oh, actually, there's one other thing. I guess, actually, I don't think I remember seeing this slide, but I'll just mention it very briefly. So you could also imagine just doing KCnHCl, which would give you the cyanohydrin, and then you could hydrolyze the cyanohydrin into the hydroxy acid. And so you might be thinking, okay, well, this is not very useful, right? Because this is a hydroxy acid. So how would this help us? Well, one way you can salvage this is you can do a PCC oxidation into the keto acid. And hopefully you guys are seeing where this is going. But once you're at the keto acid, you can do a reductive amination. So something like that. And that will give you out, right, the amine. So this is kind of a way of saying, oh, if you messed up, you accidentally put water, or if you accidentally forgot to put the ammonia in, or you can't afford it or whatever, you can just make the hydroxy acid, oxidize it, and then just do a reductive amination. Yep, cool. All right, we'll call it on there for that just to keep moving. All right, pyridines, right, are 6-membered rings. So pyridines, again, we think about a pyridine ring. A lot of ways to think about pyridine ring, right? But the main representations that I like to think about is that a pyridine ring essentially is if we took a nitrobenzene and inserted the nitro portion, so this nitro portion as an N into the ring. So if I want to consider how a pyridine should react, I should think about nitrobenzene, right? For example, nitrobenzene is a meta-director, very deactivating. If it does EAS, it's at C3. Right? Guess what? Pyridine, again, very deactivated. It is also meta-directing in the sense that if it does an EAS reaction, it does it at C3. Okay, so one way to think about pyridine is a nitrobenzene. can help you think about reactivity and how activated it is. Okay. Another way to think about it is, if we look right here, that's a CL1N, that's an imine. So if I think about an imine, right, imines are kind of like carbonyls. And so reactions that are similar to carbonyls, right, should work here too. So for example, if I wanted to add in a nucleophile, right, again, nucleophiles like to add into carbonyls, especially on a pyridine at C2. So nucleophiles love adding into that position there because it's like a carbonyl. If I kind of extend this idea, like if I kind of break the ring, you might notice that the ring is essentially an extended imine system. It's a conjugated imine system. So not only can I get the 1,2 direct addition, you guys might remember that term, but you can also get the 1,4 conjugate addition, right, where it adds in here and goes into nitrogen. So C4 and C2 are generally activated towards attack. Just remember that kinetically favored position is the C2 position. So we will see this kind of abused with the amine reactions, the pyridine reactions with nucleophiles. Is typically nucleophiles like to add into that C2 position. Okay? So we can also consider pyridine as an imine, right, or as a conjugated imine. Help us figure out how NAS reactions work. Okay. The last thing to think about is the fact that pyridine has a lone pair, but that lone pair is not conjugated, right? It's on the outside of the ring system, right? This nitrogen already has a pi bond that it's contributing to aromaticity in the pi system. So this lone pair here is actually non-aromatic, right? It's non-aromatic. It's just a lone pair. And so it is actually pretty basic, right? At least compared to a pyrrole N. So generally speaking, pyridine type ends or double bonded ends we consider to be particularly basic nitrogens. Okay, like let's say I have this here. This is an imidazole where I have a double bonded end and a single bonded end, right? Or a pyrrole N and a pyridine N, right? If I consider where 1 mole of proton is going to go, right? Again, think about what we just talked about. Pyrroles lone pair, pyrroles and lone pair is contributing to aromaticity. Pyridines is not. So pyridine has a better time picking up this proton, or that pyridine N does, as opposed to the pyrrole N. Okay. This can also help us rationalize on an imidazole where we might see, for example, like an EAS reaction, right? If we added an electrophile, because if this is a pyridine type N, remember pyridine type Ns, or on pyridine, things like to add C3, right? On pyrroles, things like to add C2. So if I have these two C2 positions, right, which one is C2 to the pyrrole N, but also C3 to the pyridine N? You betcha, you got it. The C3 is right there. So EAS generally, right? I mean, it kind of varies on the conditions too, but you can, if you had to guess EAS on a imidazole, if it were to add to carbon, very likely go to that C2 position. Very, very likely. Yeah, cool. All right, just, talk about things just because it's cool. Okay. This is even better exemplified, actually, if you think of a pyrazole, right? On a pyrazole, right? C3 positions right there. Okay. Actually, it's actually a bit of a complicated question because this is a C2. So it may not be entirely clear which one it goes to. So actually, never mind. Let's not think about that. I don't want to ruin your guys' brains as to where things would go. But anyways, it's all good. Cool. All right. So when I look at this problem here, I have a pyridine, right? Again, thinking about EAS would be here, right? NAS would be here or here, potentially. Usually it's going to be C2 because of a kinetic effect, right? Again, this is the kinetic position. It's going to add there first usually. So kinetic effect. Okay. And then if there's like an electrophile, I guess an electrophile could also attack here like a proton, but we don't really see that in the silver fine. Okay. But we have NaNH2, which some of you might instinctively think, oh, that's a nucleophile. So based on these rules, right, nucleophile, that means we're doing NAS. So in this Chichibabin reaction, right, you might instinctively do this, but that's okay. If you did that, it means you're thinking, right? You're thinking correctly in terms of what type of reaction is and where it should go. Okay, but I mean, these amino arms are not there for no reason, right? Remember, base likes proton, and base could potentially take off this proton here, right? Which, I mean, it will, and we'll actually get a cyclization like that. Yep. Now, mechanistically, this reaction is a little weird when you kind of look at it. Okay. I say it's weird because when this N- comes back down, it actually kicks off the hydrogen. Okay, so we actually, for the first time ever, have an H- leaving group, or a sodium hydride leaving group. Okay, one of the top leading chemists in heterocycles likes to call this the best synthesis, or quote unquote best synthesis of sodium amide. It just turns out that, hey, the hydride and the amine have about the same basicity, the same pKa. So it leaving, hydrogen leaving in place of nitrogen, not too crazy. The other thing that kind of can drive this reaction forward is the fact that once we do add on the amine, we do get a conjugated system, right? This nitrogen lone pair can conjugate into the ring, which is already very electron poor, right? Remember, it's very, very good, right, at doing NAS, right? Maybe not that good at doing EAS. Okay. But now that we have this electron donating group conjugated to the ring, you can imagine EAS is possible now. So kind of solving that issue we seen earlier with the pyrrole, right? Pyrrole is very good at EAS, kind of trash at NAS. So what do? We added an EWG, made the reaction a lot better. So what do we do for pyridine if it's very bad at EAS? You add an electron donating group so it becomes better. And that's what we see here. Now, generally, because this is the nitrogen that's donating electrons, or that's the atom that's doing so, this is what's going to direct. So let's actually just use a normal Chichibabin product just to kind of exemplify this. But if I have, let's say, like an NH2 here, right, this nitrogen can now direct, it's going to direct ortho and para, okay? Generally, para is the major product because of sterics reasons. So you can go there first if you want to. Yeah, cool. So very, very easy to make these 2 amino pyridines. Okay. Cool. All right, and then we can do EAS on, across from there. So maybe we add in like a HNO3, H2SO4. Technically, you wouldn't want to do this without protecting the amine a little bit, but because you guys kind of rushed through this section, it's okay. We can pretend that it's not that big of a deal. Although it kind of is. It kind of is a big deal, but it's okay. Cool. All right. Now, one last thing we'll talk about pyridines before we move on is and these guys are very, very activated towards NAS. So one thing that we can make this do to make this NAS reaction a lot better is we could add like halogens. Okay, so why is this required, or why is it better? Well, remember, in the Chichibabin, we've got to get rid of hydrogen, right? And the only reason why this is possible is because between N and H, right, the leading group is kind of obscure as to who is better. They're both about similar pKa. So it just kind of comes down to equilibrium, Le Chatelier, stuff like that, to kind of push over to the edge that H- leaving group. But if I wanted to put, like, for example, like an OME, right, which is a lower pKa than nitrogen, far much lower, or even like a CN, right? I'm not going to be able to do that with the Chichibabin process, because when I get to here, right, so I get CN here, for example, absolutely in no world does the N- come down, H falls off, right? CN is so much more stable than H, right? It's not even a competition. And so we kind of run into this issue of, okay, if I wanted to add other groups, I would have a big problem. One of the ways to get around this is to start with a chloropyridine. So whether it is at C2 or it's at C4, right? The positions that are inherently active for NAS, right? And I can just go ahead and do a substitution, right? And this is just, again, if I just think of this as a nitrobenzene, this is just an NAS with a ortho or para, right? So there's a chlorine here, it's ortho or para NO2. Okay? So nucleophile will add in very, very readily at this position here. Okay? You can also get over that issue of having that inherent, C2 selectivity usually kinetically by starting with a chloropyridine that is at the 4 position. So now when a nucleophile adds, right, it will always add to that 4 position over the 2 because we have that chlorine there that can leave. That's a better way better leaving group than a hydrogen. Yeah, cool. Now, one thought experiment that I'll give you guys to think about for a while is, well, again, EAS happens on the C3 position. So if I wanted to chlorinate, if I want to start from pyridine and chlorinate, I would end up over here. So what would be the solution to getting chlorine here? You'll really have to think about this, right? It's not the simplest problem. So think about this for a little bit. Okay. But I will tell you what, there is chemistry from 118C that you can use to solve this problem. How can we make the 2-chloropyridine instead of the 3-chloropyridine? Okay. And my one hint to you is think about the one reaction you can do at C2 and how you can modify that or modify that group that you introduce. Cool. All right. Again, for the sake of time, let's just keep moving forward just because I'm noticing I'm wasting a little bit of time. All right, cool. Moving on. So D, we have an amino acid. We have 2 moles of HCl. Remember, amino acids can exist in various charge states. One of the most important ones being the neutral form of the Zwitter ion, from which we derive the pi. Okay, but generally for these kind of questions, you want to approach, what would 2 moles of acid, how would they add to an amino acid? Generally speaking, you'll be given, if you're given acid, you'll be given the most basic form. And remember that on an amino acid, there's always an amine, and there's a carboxylic acid. So if you are starting with the basic form and adding acid, right, the most basic elements should react. So for amino acids, most of them will have an amine. So you can imagine that for sure, right, this amine will have some reaction here. Okay. Now we can also look at the R group. Right. And in the R group, we also see amines. So we know that the R group is also somewhat basic and can also participate in acting as a base and pick up these protons. Okay. If we look here again, we have nitrogens. We have nitrogen here. And carboxylic acid, right? I mean, that's an oxygen system, right? If I just think generally about what's more or less basic, right? Nitrogen's always going to be more basic than the carboxylic acid. So I know that my 2 moles are going to be consumed by this amino acid component here. So again, I'm fairly confident that this guy will protonate, so I'm not worried about that. And maybe I also know a little bit about pKa's that help me make that decision a lot more easily. Okay, but when I get to here, right, again, that imidazole system, right, which nitrogen is it that's going to consume that proton? It's really going to matter, right? Whether it's the pyrrole type N or the pyridine type N. Okay, always keep this in mind. Pyridine type N's are bases, pyrrole type N's are not. So it's the pyridine N that's going to get protonated here alongside our alpha amino amine, okay? And our carboxylic acid carboxylase has to be untouched. Now, obviously, if this were 3 moles, this would get touched because it would have to. But usually these questions are set up so that you have to kind of choose 1 or 2 out of the 3 groups to deprotonate or protonate. Okay, so this is sort of the deprotonation sequence. A deprotonation question could be like, if you started from here, right, and you did like OH minus 2 moles, and you had to figure out where were those 2 moles quench on here. Again, if we kind of think of the opposite way, right, we have oxygens and we have nitrogen. Well, actually, this is very simple, right? We have 2 oxygen species, so clearly those guys are going to protonate. That's no question about that. Right. And then we have this nitrogen species that is going to be more basic than all of them or the least acidic, so it stays positive. Okay, so kind of 2 ways to think about this problem. But you can see this kind of problem is a little boring. So usually you'll start from something that's a bit more complex and you have to think about a little more. Okay, cool. All right. There's a lot of ways amino acid questions can be asked in this section. This is just one of the ways that they can. Okay. We can also see amino acids being asked in a question similar to E, right, where we have, instead of just 1 amino acid, we have 2, we have a dipeptide, right? How can I recognize that this is a dipeptide? Little trick here. Peptide backbones will always follow the pattern NCC, NCC. You guys might remember this from bio. So if I just start from any nitrogen, for example, this nitrogen here, this NH2, and I just kind of trace NCC, NCC, right? I can see that this is a peptide chain, right? Because that's following that NCC pathway. And so we can see that we kind of crossed over a couple of these, but we can see here the amide bond, right? The true peptide bond, right? So the peptide amide bond. And since there's one of these, right, fairly confident, right? Especially since it's one in that backbone, fairly confident that's just a dipeptide. Okay, cool. So just ways to recognize peptide and just some couple things about them, right? Don't forget this is primary structure. Okay, cool. Our reagent is Edmonds reagent, right? The NCS, the isothiocyanate, or thioisocyanate, whatever it is. But anyways, Edmonds reagent. Most important thing to understand about this is that Edmonds attacks on the N-terminus side. So when I look at my amino acid, N-terminus just means the side with NH2. So it's the backbone. So it's that NCC, 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 right? Usually you'll start with an N, or start with a C, and then the opposite side will just end with the other letter. Okay, but in this case, I've written it such that N is the start point and C is the end point. Okay, and this would be our N term. So this would be our NH2N term, and this would be our COHC term. Edmonds reagent attacks on the N term side. So when I kind of trace that NCC, NCC again, I see that this is my C term, my free carboxylic acid, and then my N term here, that free amine. And so Edmonds is going to attack the amino acid on this end here. So NCC, this here is my amino acid that's going to get attacked. So I'm going to lyse that amide bond there. Now, Edmonds is super easy to predict as long as you have the structure. Okay, the structure will always look like this. Okay. This is always the structure, right? Where this is the Edmonds reagent right there, that isothiocyanate, and this here is just our amino acid. So if this is just our amino acid, our amine, our acid, this carbon here is just our R group. So whatever the R group is. So in this case, the R group on this molecule is a sort of, I'm not sure if I drew that. I think I meant to draw cysteine there, because I think methionine is 2 carbons in a methyl. Yeah, I think I meant for this to be cysteine, but I just forgot to erase the methyl. But anyways, it's fine. Methylated cysteine. That's okay. Yeah. Now you're welcome to draw the other amino acid if you want to. If you want brownie points. Okay. In this case, this is a glutamine. But I don't think you would get in trouble if you did, or you wouldn't lose any points if you forgot to put that on there. Okay, but you could if you wanted to. Cool. So Edmonds reagent, find that NCC backbone, right? The NH2 of the NCC is what Edmonds likes to attack. Okay. And again, that NCC, that peptide bond, really good ways of figuring out that you have a dipeptide, right? That you're working with that. Another great question you can do with dipeptides is just a complete hydrolysis, right? You could do 1 normal HCl overnight, right? This is part of sequencing, right? And this would just break the peptide bond. So you could potentially be given a question where you just kind of break the peptide bond and show off your 2 amino acids. Okay, just like this. Okay. Now, one really important thing to remember is that hydrolysis is not just like, it's not like hydrolysis knows this is a protein and it only breaks amide bonds. You will break every type of acyl bond you can think of. So for example, on glutamine, in hydrolysis, you'll actually also can crack this amide bond here as well, right? Because, I mean, if you can crack the backbone amide bond, you should definitely be able to crack side chain bonds, okay? And so our glutamine actually transforms into a glutamic acid. Okay, so this is actually really important when you take biochem, when you're doing sequencing of proteins, because this is sort of like a false signal, right? If every single glutamine or asparagine hydrolyzes into its aspartic or glutamic acid counterpart, then we truly will never know just right off the bat, right, how much aspartic or how much glutamine we actually have. We'll have to use different tests. So if I remember correctly, there is a different letter code you use for asparagine, aspartic acid, glutamine, glutamic acid when you are referring to them after hydrolysis for this very reason, right? I believe it's like Q and it's Q and something, and like Q and Y or something like that, I think. I'm not sure. But I know you definitely use a Q. Wait, do you? I don't remember. It's fine. I'm not a biochemist, so it doesn't matter. But cool little fact to be aware of, right? And we can explain it with chemistry that we know, right? The fact that we're able to hydrolyze this peptide bond means that we should also hydrolyze this one too. Imagine if this were a methyl ester, this is also gone, right? To then form an acid. Okay, so just keep in mind, like, look for these things. Look for things that could potentially hydrolyze, not only just the peptide bonds. Okay, cool. All right, call it there on that one. Moving on. All right, you see this, you know what it is, right? This is the Gabriel reagent, especially when we're adding in the bromomalonate ester, right? We know this is an amino acid synthesis. We can confirm that with base and malonate ester, base and alkyl halide, and then acid hydrolysis. You can tell how much fun I was having drawing the H and then putting the 3 as a subscript and then putting the positive as a superscript. I hate doing that. It takes so long on my keyboard. Anyways, if I just want to quickly solve this, I mean, this is just an amino acid synthesis. Okay, where this is just the R group. So yeah, I definitely messed up on this one too, kind of on the one above. Like I definitely meant for it to be wherever it is. Yeah, I meant this to be, I think, a cysteine. But anyways, okay, so this is methionine. This is what this is forming. Okay. So again, just look out for these key parts here. Look for the alkyl halide. The alkyl halide is what defines the amino acid for you. Right. So you can just kind of skip forward. It takes us in a second to do. Cool. All right. And again, once again, be careful because there's many different ways to represent these molecules. For example, maybe you might get something like this, where you get an ester with a bromide on it, right? And you're doing your addition in. Right, so you'll get right this with all the crap on it, all that, right? Ester, right? And you're doing then when you do your hydrolysis, all that nonsense, right? Hydrolysis will get rid of the ring, get rid of one of the esters, turn one ester into an acid, right? So it gets here, and then don't forget this is also an acyl group, so you can go ahead and hydrolyze there to make the acid as well. Okay, so always look out for those extra acid groups that can hydrolyze potentially, right? Don't skimp out on them. Cool. All right, moving on. G, we have, looks like 2 keto esters, amine, and an aldehyde, Hantzsch pyridine synthesis, right? And so recall the way that you kind of set up a Hantzsch, right? So you kind of draw right? You kind of draw your ketones facing each other or sort of facing this amine here. And then the aldehyde is kind of hanging out right here, right? And so this all comes together to form a 6-membered ring. So in this method, initially you get a dihydropyridine, right? So not an aromatized pyridine, but we heat all this together and we get this dihydropyridine. And then we can do a couple things, right? One is we can oxidize this usually with HNO3. There's so many things that can do this oxidation, honestly. It's not something that worth worrying about. But anything can do it, really. You can cough on it and it will probably, actually, I do want to talk about this because it is relevant. But a really funny way that you could reduce this, I guess if you wanted to be really cheeky and you wanted to I don't know, impress your TA or something, this here, we call it a Hantzsch ester, right? This is a Hantzsch ester. Hantzsch esters are the synthetic equivalent to NADPH or NADH, which, not gonna lie, I don't remember the full structure for. But generally speaking, NADH, what it is, so what's going on? Okay. Oh, what the heck? Oh, there we go. Sorry. Lost my screen for a second. But NADH, right? It's a nicotinamide. So what does nicotinamide look like? It looks like this. Yeah. Well, actually, this is nicotine. Sorry, this is nicotine. But the nicotinamide, dihydronicotinamide, I suppose, looks like this, right? And so this is sort of, this is what NADH is, right? But the way that it works, right, is it transfers hydrides in the cell via aromatization, right? Because this will turn into pyridine, right? Won't it? And so it's this action here, right? That's the fact that this is getting kicked off, turning into this pyridine. That's what's allowing for these reductions to happen with NADH, right? Now this is NAD plus, right? Apologize, I don't know the full name. I should really look. Oh, it's nicotinamide adenine dinucleotide. All right, cool. I did not know that. And I learn something new every day, right? I bet all the biologists are like yelling, like, oh, of course I knew that. Of course you should know that. But anyways, I guess a really cheeky way, if you wanted to like get on your TA's nerves, or just kind of make them laugh, is you can probably put like a carbonyl or something here, just to be funny, right? And then probably put like an enzyme or something. Actually, this is something that I would definitely do just to fuck with my TA. You put like a carbonyl, or like, sorry, not like an ester, but like a ketone, and an enzyme, and that could functionalize your oxidation, right? Just funny jokes, right? These are just funny jokes to tell. But anyways, anything can really oxidize this. HNO3 is what you usually use. Yeah. And then if you wanted to, we could decarboxylate. I believe this is the sequence. So that we get this 1,3,5 trisubpyridine. Okay, so there's kind of 3 different sections that this could possibly stop at, depending on where you stop it, right? As we can see here, we're just doing one step, so you can see that we're stopping at the dihydropyridine. This is actually very intentional. This was not a mistake. This is because this here is a drug, billion-dollar drug right here. Okay. So this part is pretty easy to set up, because where it gets kind of hard is right here, because there's like an NO2 on this, kind of gets in the way. I'll just draw this with a comically long bond. Okay. There's a methyl here, so that's why I know to put methyls here. Okay. But we can make this dihydropyridine. But if I added in a second step like HNO3, right, I could go to the pyridine. So if step 2 was HNO3, or that cheeky carbonyl with an enzyme, right, then I could go to the pyridine. And if I wanted to, I could also even decarboxylate if I did a third step. So you could potentially get all the way down to here. Just depends on how many steps you do, right? But in this case, we only did one step, so we're all the way back here. Okay, so just be mindful of that. If you just have to note card, you'll never get this question wrong. Now, in synthesis, a very cheeky way to kind of get around this dihydropyridine if you don't need it, is to actually use hydroxylamine. Okay, and the reason for that is because when you have hydroxylamine, you've actually installed the oxidation state you need. If you think about it, oxidizing here, or not really oxidizing, but to get the pyridine transformation, you just have to lose water, right? H gets taken off as a proton, and then you lose OH minus. So formally, all you're losing is water here. You don't have to just dehydrate it, right? Heating it will just do it. Okay. So if you want to, in synthesis, if you want to get around making the dihydropyridine, you want to go instantly from the bake mix all the way into the pyridine itself. Just use hydroxylamine, NH2OH, right? Impress your TA and your professors by doing that. Okay. Cool. All right. That's all I'm going to talk about for that. There's many, many, many ways of making pyridines. I'm just so sad. Heterocycles is what I'm going to grad school for. And I was so excited and prepared to talk so much about it. But I mean, everyone's so tired, and we kind of sped run through this in the course. So, can't win every battle, but, oh well, whatever. Anyways, one last thing. So obviously you can make pyridines, but how do you know how to make them, right? What's something you can do? If it's, for example, a Hantzsch, one thing about Hantzsch is that Hantzsch has to be symmetric, right? These two R groups have to be the same. So if you notice your pyridine right? I mean, it has to, right? But it'll have symmetric groups. You can always cut on either side of the heteroatom to kind of, quote unquote, release it so that you can get to this part here, right? This can be NH3 or NH2OH. I'm very cheeky, so I'm going to put NH2OH. Okay. But we'll have R here and we'll have R here, right? Where we cut that amine from, just adding carbonyls. Okay. Now remember, this carbon that bonds these two carbonyls together, this sort of like back carbon, the carbon opposite the nitrogen, used to be an aldehyde. So we can even cut that out too. Right, so we get this here. So in this case, we would have this here, just, oh, sorry, it should be R prime. We'll have R prime. And then remember, we need the beta ketoesters, right? So those are going to be there, the beta ketoester. So very easy to retrosynthetically figure out what components made your pyridine. You can imagine to kind of accumulate all the information, you could be given like a carboxylic acid, asked to turn it into an ester, or or forced to think of that, do a Claisen, and then potentially, right, do the pyridine synthesis, right, to make a 1,3. And then, if you wanted to, right, you do have some activation. You could get some C3, C5, right, EAS. So, just to tack on another step here, you could get some like electrophile added on if you wanted to. So, synthetic ideas. Cool. All right, we'll call it there just for that, just for time's sake. H, so a little bit of old material. We have SOCl2 that's going to turn this into Cl, right? And now this is nasal chloride that's capable of doing EAS when we add in the AlCl3. So AlCl3 will add here. All this will leave, right? And what we'll get out is the acylium, right? And so recall that on indoles, right? Indoles kind of break the rule of the heterocyclopentadienes, right? Based on what we've told you, right? It's very tempting to put it here, but in fact, indoles attack at C3. So in fact, actually, we'll get the attack here. One, two, three, four, five, six. Okay. Just like that. Okay. And then the H2PD step is going to get rid of the benzyl group. Right? It's going to get rid of that. Okay. So why is it that indole does C3 instead of C2? What's usually the commonly invoked reason for that? Well, the reason for this is that this is not just, any kind of indole, or sorry, any kind of pyrrole where we just have like, two pi bonds that, when we think about how many resonance forms you get, this gets more, right? When you do C2 attack. This is a benzannulated or benzene pyrrole. So not only do we have to care about the electron movement in the ring of the 5-membered ring, but also have to consider what that means for the benzene. Remember, benzene is the poster child of aromaticity, right? It doesn't want to react at all. It doesn't want to be disturbed at all. So when we think about electron movement to attack at, for example, C2, right? Electrons have to push into the ring, the benzene ring, and break that benzene ring, right? You can see that's breaking this. Like the C2 intermediate would have to look like this if it attacked on C2. Which that's very, very bad. So in an attempt to avoid breaking that, right, the easiest way to think about this is that this pi bond here, or the pi bond that should be there, right, is essentially inert. It's not even existent, right? It's in the benzene ring. So the only pi bond that we have is this pi bond here, which acts more like an enamine than a pyrrole, right? So it attacks at C3 rather than C2. Okay, so probably the best way to think about it is that C2 would require breaking aromaticity. Very, very bad. Okay, C3 wouldn't require that. C3 can leave the benzene alone. That's very, very good. Okay, cool. All right. Now, obviously, if we had to go another EAS, it would definitely go here. But what's really, really interesting about the indole is that, in fact, if you were to add another electrophile, weirdly enough, the electrophile will actually add to C3 first, right? That's how big the preference is. So the electrophile will indeed attack at the C3 position, but this substituent will actually rearrange. Okay. And for two reasons, right? One is that by rearranging, actually, I guess really one reason. The second one was kind of stupid, but it will rearrange so that it will, okay, that we will get, I guess this, whatever, it's fine. We'll see rearrangement because we can ultimately restore aromaticity. Okay. So in fact, that preference for C3 is so big, right? It's so favorable for the indole. Even when there's already something occupied there, it will go C3, but we will get a rearrangement afterwards to get to that C2 position. Again, not interrupting the benzene, and then we can re-aromatize. Okay, now kind of skipped on a couple protonation steps there. Oh, actually, I guess I realized I could have just done that. That would have avoided the issue that I had, but that's okay. I'm just an idiot. But yeah, cool. All right, so cool little thing here. This could be a great mechanism question, possibly, or explanation question, right? Cool. All right. So that's indole. I think that's all you really need to know for indole. Not much more than that. Cool. All right. We have dichloronitrobenzene, okay, where one chlorine is ortho to N2, the other one is meta. Recall that the ortho para chlorines are always activated when they're orthopara to NO2. So when I think of an amino acid, we have a carboxylic acid and amine. Amine is more nucleophilic. That guy is going to substitute there. Okay, so ultimately what we'll get is this here. Okay. Now, originally I wanted to write the problem with another NO2 here so that you could, attack there too as well, but whatever. That was just something I was thinking of. Okay, cool. Now recall that this chlorine can still react, but because it's meta, it would have to react via benzene, which benzene requires much more rigorous, much more, terrible conditions. So, sorry, benzene, not benzene. Cool. All right, moving on. J, this is this is actually a precursor. This is tryptamine. If I wanted to, I can methylate it, as we'll see in a second. So excess formaldehyde in NADPH3CN, reductive amination, right? What I was kind of trying to key you guys into is that not only can you do, right, so one addition into the aminium, right, of that formaldehyde, and then do a reduction, right, into the CH3, so you can actually do this twice, right, when you have an excess of the formaldehyde. So, right, that one addition, and then reduce it into CH3. So this makes DMT psychoactive, right? Right, the crazy drugs. Dr. Olson at Davis, I believe, works on psychedelics. Cool. All right. So that's the predictive products. We got through a lot of material, most of what we wanted to talk about. But again, we still have more predictive products. I think it's been about an hour now. So damn, that took a while, but we'll kind of get through this a little bit quicker. Probably gonna look at 2 hours for this video though, so a little womp womp on my end, but that's okay. Cool. All right, moving into the mechanisms. So mechanisms, for the most part, in your notes, so not much to stress about here. This is just Paul Knorr. So essentially, the idea is, right? Well, let's say this is protonated, right? Okay, I guess I'll just kind of do a generic one for now, but you'll get an addition of the amine, right? Get something like that. You can get a proton transfer. So essentially, something will take this proton, this will take a proton, right? Actually, I guess you could, if you wanted to, you could do something like that. The proton, I mean, it's pretty far, so that is reasonable. Right? It's really it's geminal atoms that can't deprotonate each other, right? But once we have this, right, this can go ahead and attack there. So we've essentially formed our 5-member ring, right? Now it's just a matter of subsequent dehydrations, right? So this will get protonated and we'll lose water here. Okay. And then this will go and get protonated. So OH2 plus, and then we'll lose water here. Okay, so polymer is not that bad. Very, very straightforward dehydration. In this case, we just had, the R groups were a little weird, right? They were just the rings, but they would have gotten in the way. That's why I don't want to draw them. Okay, so this looked like that. Okay, cool. So polymer should not be too bad for majority of you guys. Yeah, cool. All right. This is again straight from the notes, diazotization. So remember that this together will make the NO plus cation. Definitely review how to make that, right? That's this turning into water, and this will kick it out. Right, so we make the nitrosyl cation. Okay, this can go ahead and attack the nitrosyl cation. Right, and then essentially, because I don't want to draw this out, I'll just say it. I mean, we have H2 here, we have O here. We have essentially want to do proton transfers to the point where we get to here. So this water molecule here. Okay, to kind of draw this out stepwise, right? You'll have someone take this proton, right? Protonate here. And then someone will take this proton, electrons will move like that, so that you get to here. And then this will just protonate one more time. Okay, so we get to here. So that's essentially how the arrows work for that. I apologize. I know I'm doing these very fast, but again, these are in your notes too. So just look at your notes, right? To get the full uncensored mechanism. But from here, right, this can shoot down, kick off the water, we get our diazonium. Now, I mentioned earlier, I asked a question of how could we possibly activate the C2 position on a Chichibabin product, an aminopyridine, to have different groups other than an amino group? Because remember, amino is the only thing. NH2 minus is the only thing that can replace H minus. Well, we can turn the NH2 into N2. And N2 is the best leaving group in the world, right? We can switch this out for a lot of things. So if I wanted to, I could switch this for a halide, right? Using copper salts. Right, I could switch this for water. If I just want to do H3O plus, right? I could switch this for, because of hydrogen if I wanted to, but that'd be kind of weird. I could switch this for a cyanide, right? I've incredibly increased my versatility of things I could add here. I mean, again, I can even put a halogen here and then do all my sort of halogenation reactions that you would expect, like a better NAS, right? So just a way to activate that position. That this is the answer to that. Okay, cool. All right. Moving on, we have here look like an ester turning into an amide. So the mild acid, I know a couple of you might be like, whoa, we're not supposed to have acid, right? That was the midterm 1 question. I just wrote that so that you could do this, right, without having to worry about it. But you can just go ahead and add that in, right? And from here, this is just additional elimination, right? If you use a proton, it makes it easier. So you could do the isomerization, you could do protonation, right? You can do an attack, right? Additional elimination, blah, blah, blah. Again, notes type reaction. Okay, cool. I hope your mechanism isn't too bad, mostly just within the, I mean, usually it's like 1 or 2 new ones and then an old one. So probably something similar to this, where this is, this is midterm 4 material, and then one from an older midterm, and then one from the first midterm, right? So something like that. Cool. All right. Synthesis, right? It's where we prosper. So a couple different synthetic strategies. We've already went over a couple, but we'll go over them again. There's a couple ideas I have for what are the possible syntheses. 25, 26 related. I can't really guarantee that it will be that, but I'm hoping that just cross our fingers. But one of them is very great option is the amino acid, right? We learned 3 ways to make amino acids, right? There's Strecker, HVC, and then there's Gabriel. Right, so those are 3 ways that we learned. And so this synthesis actually was designed so that you could do any of these 3, right? As long as you know what to recognize. For example, we talked about Strecker. Strecker just means that the V of the amino acid just originally came from an aldehyde. Okay? So this here just used to be an aldehyde. Remember, to kind of do this would be the KCN NH3 HCl, right? And then we do a hydrolysis. Right, that's what we would do to get to there. So as long as you know how to trace it back, you can totally use it. Okay. Now, if we look at our starting material, it's a toluene. So it's all this here. What we're adding in is this carbon bond. Right, we're adding this carbon bond. So we're forming the CC bond here. So best CC bond reaction since the beginning of time is the Grignard. Just remember, Grignard gives us alcohols. So if I take off that oxidation state, so say this was a PCC reaction, I can see here that, oh, what I added in was a formaldehyde. Right, so this is like an organometallic. What I added in was like a formaldehyde. Okay, organometallic is really easy to make on the benzylic position. You just use N-butylate. Okay, so this could be your pathway from Strecker or through Strecker, right? If you decide to use Strecker, totally possible. Okay. HVZ would just be that, if I have an amino acid, right, HVZ would just note that, okay, the nitrogen used to be a bromine, and then bromine just used to be a hydrogen. So HVZ is that P-trace Br2 reaction that you can replace that bromine with an amine, make an amino acid. All that really means is that tracing back, we kind of go back to this here, the carboxylic acid, right? The carboxylic acid itself, we can trace back to an alcohol via Jones, right? And then again, we ask the same question, right? The toluene portion is the same. All we're adding in is a CC mu CC bond, where the fragment is 2 carbons and an alcohol, right? That fragment belongs to epoxide. So essentially, if I choose to epoxidate, or if I choose to add an epoxide, 1, 2, alcohol, I can do Jones, right? And then I can do HVZ, which would be, because I'm very, very lazy right now. Right, we just do that, and that will get us to over here. Okay, so you can do that if you wanted to. Okay. The last thing you could do is to Gabriel, which is kind of like the cheat code here, because Gabriel assumes that the acid and the amine come from that large reagent, right? This here, right, the phthalimide attached to the malonic ester. Okay, and that the R group comes from an alkyl halide. So adding these in together, so putting in some base and then doing H2O plus and heat, right? That will give you the product, right? That will give you this guy here. So how do we make the bromide from the toluene? That's just benzylic bromination, right? So that would just be NBS. So this is sort of like the cheat code, right? Because you can just kind of throw in this reagent, right? This huge goddamn reagent, just throw it in and just say, hey, that's just going to add to the bromide, right? When you add in some base. So kind of a cheat code, but you can get away with it in this class if you wanted to. So truly the shortest synth is this Gabriel synth. But you can do any one you want to. I really don't care, as long as you stick to the methods that you know. Okay? So again, main point of this was to go through the signaling elements for how do I know which mechanism is going to be present. Okay, cool. All right. So moving on. This synthesis here, we have a diester turning into a furan. like I mentioned with the pyridine, right? I mentioned that the pyridine, if I wanted to go backwards, very easy way is to cut that heteroatom out and replace where I cut with carbonyls. Same thing with 5-member rings. Just cut that heteroatom out. Right? P2O5 is usually the reagent used. Okay. And where I cut that oxygen out from, right, because that's just PO5, is going to be carbonyls. So 1,4-dicarbonyls are going to be your key to the 5-member rings. That's what we have here. Okay. So we can trace back to here. We can draw this nice if we want to. It's totally up to you. Okay. Now, looking at this, it may not be totally clear how to move forward, but one thing we might notice is that we have this diester here, and we have a ring compound here, right? Hopefully you can see what's going on here, but clearly this diester is meant to cyclize and self-Claisen so that we can get this ring here. So I can almost even, in a very shocking set of moves here, actually move a little forward. Okay. So I'll just do this here. And I'll get to this point here. Okay, cool. Now, one thing that I always mention, or I mentioned a lot in the last chapter, or last midterm, is that when you're doing a synthesis that ends with a ketone of some kind, or might end with like a carboxylic acid, back in that midterm 3 context, usually what that meant was you made it from some kind of beta ketoester, right, and you decarb off the ester. Right. Recall that the whole point of this ester being here, right, next to this ketone, is to make this position more acidic, right? And so it makes it easier to alkylate stuff. So wherever you see branching, right, that is indicative of the presence, or usually the indicative of the present place an ester could have presided before it got decarbed off. So if I assume that a decarboxylation event occurred, right, after adding in a branch, and look at all these positions, I'm just looking for a position that has a branch on it. And I'm going to say the ester was there, so it helped it add in that branch, right? So when you look at all these positions, this carbon has a branch on it. Right? So I'm going to assume that there used to be an ester here, right? Because that ester helps facilitate the addition of that branch. Okay, so that's the logic that we're employing here, right? Using this, using the branch to guide us, because that's the whole point of the ester, right? It's an auxiliary, right? It makes it easier to add in these carbon chains. Okay, cool. All right. Now that we have that on, we got to figure out what this carbon chain is. And again, if I look at the fragment, we're making a CC bond where I'm adding a fragment that has 2 carbons and an oxygen, right? This is indicative of an epoxide, but epoxides, right, those come from alcohols. So we know that this was some kind of PCC oxidation. I'll put E here for ester. And so from here to here, it's just base, then an epoxide, right? If this is 1, this is 2. This is 1, this is 2. On 2, there is a methyl. As you can see that. Okay. And so this is your way of making the 1,4-dicarbonyl from Claisen condensation. Right? Now, obviously, I made this a bit more complicated because I did it intramolecular. That's not required, right? You could have also have just done a non-intramolecular variant of this problem to form this here, get rid of this, and then do your coupling with P2O5, P2S5, whatever you want. Okay, up to you. Cool. Now, again, if I wanted to, if I did EAS from here, I could have, it would have to go to this position. That's the only position that's open. So electrophile would have to go there, right? Because both my C2s, my C2, my C5 are closed, and this C3 has, it's also closed. So that electron will go to C4 if I wanted to add it in. Cool. All right, so these are kind of like beginner sort of, warm me up type syntheses, kind of help you think about what are some things you can do. I think one of the most important things to kind of look out for is any way you can make an intermediate a different way, maybe using old material. For example, nothing here really, stands out as, oh, I could have made this with old material, in my opinion. But like, if I think back to like amino acid synthesis, for example, like aldehyde, right? That's super important for Strecker. Many ways to make aldehydes, right? One of them being like double, right? That's a chapter 20 reaction. It's a great way to be asked on how to make a some kind of molecule, is you have to dibble it to the to the aldehyde, and then you could do like Strecker synthesis. Oop, not writing that. Right, you could do like a Strecker synthesis, right? Cool. All right, so 2 more syntheses on the way, right? We have still the practice midterm 2 that we're going to have to kind of blaze through. It's going to finish in an hour. But, looking at these, right, it's a little bit harder, but we can get through it. We can get through it. All right, explanations. Explain why pyrrole is protonated at the alpha carbon and not at nitrogen. So I mentioned that, pyrrole, again, usually is not going to be basic at all, right? But you can force it to do so, right? You can get it to protonate. It's actually not as difficult as I said it is. Generally, it's difficult, but not that difficult. But if you do, it protonates at C2, right? So I drew this a little bit bad, but I can draw this like this, right? So you can protonate it like this. And that's usually what happens. So the question becomes, why is it that it's protonating here at C2 and not just on the nitrogen, right? Because technically the nitrogen, that's where the electrons are, right? When we draw it, but it's not where we see the protonation. So your guys' job is to figure out why that's the case. If you kind of stare at this long enough, you might start to see things. Particularly what I look for is stability, right? If we're going to protonate on carbon, there must be some stability factor. Looking for things that might be stable. I see here that there's a conjugated system, so it definitely looks like we got resonance. I mean, this N cation, this iminium is probably not very happy, so electrons are resonating in. So the ability to resonate electrons, that looks like very good. If I try to do the same thing here, this is an sp3n, so this can't resonate at all. And these 2 pi bonds, sure, they can resonate, but they don't delocalize the charge. Right? So yes, we do get resonance here, but we don't get delocalization of that cation, just like we would here, right? If I draw the resonance form of this, right, the cation is delocalized to this position, right? So there's delocalization charge, but if I delocalize on here, right, I don't really get delocalization. If anything, I get 2 cations next to each other, which is very, very bad. Okay, this is very, very bad. Okay, so the reason why we see protonation alpha carbon is that the resonating system is more stable than protonating N, which is a non-resonating localized system. Okay, cool. All right. Here, explain why this would not work. Include a solution. We have an amino acid. Amino acids, like if we think about them having an N term and an O term, or COH term, right? If I think about what's more nucleophilic, this is going to be nitrogen. So if I look at this is trying to make me believe that the carboxylic acid reacts first. No way, Jose. It is always reacting on nitrogen first. So this is the CBZ, so I'm just going to annotate it as CBZ, but this would be the actual product, right? The way that we get a selective addition onto the carboxylic acid over the amine is by doing a Fischer esterification. Okay, so why is it that doing Fischer, which is sort of like the acid version of this question, right? Why is this better? Well, 2 reasons. One, the amine in acid will protonate, so it will essentially defunctionalize itself. It'll be NH3 plus, no lone pair, right? Nothing to worry about. The other thing is that the acid can activate the carbonyl, right? Make it much more prone to attack by the alcohol due to substitution. So this is our way of getting around this problem, right? If you want to selectively protect them on carboxylic acid, then just do a Fischer esterification. Okay, amine will always win the nucleophilic battle, right? There's no way to really beat it on that front. Cool. All right. All right, so just going to do a couple of these vocabs and, kind of move on our way. This is Chichibabin. So Chichibabin, loss of NaH, right? These guys are Zwitter ions or charged molecules, I guess. Oh yeah, Zwitter ions. Why is it Zwitter ion? Because I specifically wrote charged molecules that are neutral. That's exactly what a Zwitter ion is. Okay? The pH at which is this dominance is called the pi. Right? Reaction of 1 bromo or ethylbenzene with NaOH at a high temperature. So this kind of just tells you that this is a benzene type reaction, high temperature, high pressure, no EWG. Remember, benzene results in this pi bond here, which will give you these 2 products here, the para and the meta. So para, meta, and we'll get a mixture of those 2 products, right? No directing effect, really. That can help us choose one product over the other. Cool. All right. Okay, so protonation state, this may not be everyone's favorite question. Or maybe it might be actually because these are a little bit easier. I have a little trick for these that makes them, in my opinion, a bit easier, to do these very fast. And what that trick involves is the pKa's. So the pKa's of every single molecule is a 50-50, right? So 2.1 for the carboxylate. This is 50% the basic form and 50% the acidic form. So as you move up on the pH scale past 2.2, right, you enter the basic region of a pKa. And as you move below the pKa, so below 2.2, you should start to enter the acidic region of that amino acid. So by using that logic that, below 2.2 would be the acidic region for that and above would be the basic, by plotting whatever pHs we're at against the pKa, we can tell what form the molecule should be in. So to kind of put this into practice, let's say that I have all my pKa's here. All I have to do to figure out what this looks like at pH 1 is to plot where 1 is against all these pKa's. So 1 would be here, here, and here. It's completely acidic. So every single group should be in its acid form, right? Should have its proton. Right? Remember, amines protonate to positive, right? Oxygens stay at OH or O minus. So pH 1, this is what this looks like. Okay. I can now plot 7.4, which I can just call 7, just for the sake of, just write this down really quickly. And I can see that for the carboxylate, it'll be in the basic form. But, right, these two will still stay in their acid form. Okay. Again, super quick, just by plotting where these pHs are against the pKa's. Super, super easy. Right. Last thing I could do is plot 10. So that would be here, here, and here. I know this is super close, but again, we're looking for predominant form anyway, so we will be fine. Okay. And so what we get, should be this here. Cool. So very, very quickly, we did that all in like a minute just by understanding this little trick. So protonation state, super, super simple. Don't worry about memorizing or remembering what everything means. Again, everything's got a trick to it. This is the trick, right? So you just plot those pHs against the pKa, solve this in a minute, move on with your day. PI is a little more, it's a little more stress inducing though, because, you could memorize the whole acidic, basic, we know what to do. The way that I do these very quickly so that I don't have to stress about them is I kind of look at the forms that I've already drawn and I look to see if I hit gold. What I mean by hit gold is, did I draw a neutral form anywhere? So I look in here, the overall charge is +1, so I did not strike gold here. I look in here, overall charge is -1, did I strike gold in here? But when I look here, I see that I hit gold, right? I hit a neutral form. So I did end up drawing the neutral form of tyrosine here, and neutral form exists at 7.4. So I then just look at the pKa's and I look for where 7.4 would land into, right? Would it land between 2.2 and 9 or 9.1 and 10? Clearly it's landing here, 2.2 and 9.1. So I know that the PI therefore must be then whatever is between these two, since a dominant form of the amino acid being neutral to switterion is at 7.4, right? Now, I don't know if it's 50-50 at 7.4, but I know that's a dominant form. So I know to just take the PI here and move on with my day. So this would be 11.3. I think that's 5.65 when it's divided by 2, right? Divided by 2 would give this. So 5.65 would be our PI. Okay. So use your forms to your advantage. They might help you out, right? They might give you what you need. In the event that they don't, like let's say that the question is just straight up, what's the PI of this guy? And you just have to figure it out, right? Just got to do it. You can just very quickly, jot down the amino acid. One trick that I like to use is I start with the most acidic form. So I'll do something like this, and then depending on what is this, I'll make sure it's in this acidic form, right? And then I will just move up. Right? At worst, an amino acid has 3 pKa's. Start with the lowest, so possibly 2.1. Right? Usually that controls the carboxylic acid. Right? So you can do that. and then move up again. Now this is where it'll depend if this is age as an acidic amino acid or basic, but choose the next highest number. So the number that is greater than 2.1, right? But it's less than whatever the last number is. So we'll call it M. I don't know what it is, so we'll just call it M, right? But just do that one, right? Draw the form of that. You can just do that. I mean, if you're lucky and you just hit the neutral form, you don't have to draw all of them, right? Just draw up to the neutral form so you know which two pKa's to look at. So like, let's say this is the neutral form here, right? Let's say that's a neutral form. I don't need to draw this, right? I just need to know what this pKa is and this one is. That's the midpoint of that will tell me the pI. Okay, cool. All right. So these questions here, just do them first. So easy, right? Don't waste your time. Super simple. Just get them out of the way. Okay, cool. All right. My little spiel on amino acids. Moving on, circle the most acidic molecule. So we have amines here. Most acidic is going to be the one that has, the lone pair is stable after it receives it. So one thing you can do is kind of draw lone pairs in here and think about which lone pair would be the most stable, right? If you want to, you can spend all night thinking about this. But when I kind of look at all these lone pairs, this one is a pyrrole lone pair, which we just talked about, hyperacidic, right? Super acidic, because it's counting towards aromaticity, right? It affords aromaticity. So clearly this guy is the most acidic. Cool. Moving on, circle the most acidic molecule. So I kind of drawn out the ages here so you can see what to look for. Recall that EWGs increase acidity, EDGs decrease them. Okay. When I'm looking at these, I see an EDG, I get rid of that. Remember, the pyridine nitrogen is essentially an NO2, which is like an EWG. So you can kind of tell that the point of this question, hopefully you can tell now, is to kind of get you to point towards the amines here, or the pyridines here, because again, these are essentially just EWGs. Remember that ortho-para positions are the special positions when it comes to reactivity on pyridines. And even actually, if you just think about this, right, if I put a minus here versus here, right, which one do you guys think is more capable of interacting with the pyridine N, right? You can see here that this would resonate very easily. You can see here this would not, right, have a very easy time resonating into the N. So the ortho, right, and really the para as well, ortho or para pyridine, or methyl pyridine would be very acidic versus the meta. Okay, cool. Now, one thing to note here is that this position is actually super acidic because, again, if you think about this as sort of like a extended imine system or even just an imine, right? Taking off a proton from this position is like taking off an alpha proton, right? It's like making an enolate. So obviously, we're not going to talk about this, which makes me a little sad, but we can actually invoke enolate chemistry from these methyl pyridines because this is essentially an enolate here. Right, that's completely an enolate. That's why it's so acidic too. So you can do some cool chemistry, but again, not the time or the place. Womp. Cool. All right. Moving on, circle the sugar that bubbles in response to HNO3. So bubbles means CO2. CO2 means ketose. So not a ketose or aldose. This is an aldose. This has CH2OH on the anomeric, so that's a ketose. Right, there's an H here. So this is a glycoside. I mean, it wouldn't even bubble, right? Because it's a glycoside, right? You wouldn't be able to destroy the carbonyl. So even if it were a ketose, it wouldn't matter, right? If they were this, it wouldn't matter at all. Yeah, cool. All right, so there's that. This question already got asked, though, I think, on the last midterm. I didn't know that, so probably not very likely to be asked. Cool. All right. So there we have it. That's the exam. Hopefully that wasn't too bad. You know what? I'm going to quickly skip NMR. Let's just do the other exam, and then we'll come back to NMR at the end. Cool. Let's speed run this in 30-ish minutes, hopefully. Sorry, give me 1 second. Hey guys, I just took a quick little break, as you all should, honestly. Always great to take a break. We're going to go ahead. We're going to pound through this real quick. Again, this midterm, definitely harder, but incorporates a lot, much more breadth of material, a lot more coverage, just straight up, all the reactions. So just get right into it. So we have here, looks like a furan, carboxylic acid, nitrile, NH3 and heat, right? That's going to react with carboxylic acid to make a primary amide. And this here, right? NaOH-Br2, that's the Hoffman reaction, right? Which remember, whole point of that is it kind of replaces so if I had like an amide here, right? It replaces that primary amide, by the way. So primary amide, it's got to be primary amide. This is that with NH2, right? So we make this amino furan. Okay? So old reaction, right? Black from the past, that first midterm right there. These compounds are actually really interesting. These amino heterocyclopentadienes, very, very juiced up, right? They're on one hand juiced up by the heteroatom itself, and then doubly juiced up by that neo EDG. So these guys are hyper nucleophiles. In fact, they react very quickly with oxygen, and some of these can turn into what we call butanolides. Butanolides, very, very dangerous compounds. There was a drug that was a butanolide. Forgot the it's like Vivax or something, and it was basically killing people when it was on the market because it was reacting with oxygen in the body, or it was reacting with radicals in the body and doing kind of crazy things. But yeah, cool. So we can make this aminocyanofuran. Yes, the cyano part kind of hangs out. It's also very important actually. You need EWGs on a ring if you want to on like a furan ring if you want to add an EDG. But just cool little facts. Cool. All right, moving on. B, we have an NH2 of aniline that we can turn into N2 plus, the best leaving group in the world, right? And that second step, we use a nucleophile. Remember when benzene is the nucleophile, we usually get a paracouple so that we get the diazosalt. Okay. And in the second step, we have, looks like a 1, 2, 3, 4, we have a 1, 4 dicarbonyl. That's just going to cyclize on the amine to make a pyrrole. Okay, so that's very easy. We'll just make a pyrrole here. Okay, 1, 2, 3, and 4. Looks like on 1 and 4 we have methyls. Okay. Cool. So we can make these sort of like, what do we even call this? N-phenyl, N-azo di pyrrole or something like that. Cool. All right. Moving on, we have, looks like a beta-keto ester, hydroxylamine, and aldehyde. Remember, hydroxylamine is our sort of cheat code to instantly go to the pyridine, no questions asked. Remember, the esters will go here. Right? If there's an aldehyde group, we'll go on this position, but it's just 2 H's, so I'll leave an H here. And then it looks like we did a phenyl ketone. So we'll have phenols here for that ketone, right? We have that phenyl is just that ring right there. Okay. We did have the decarb sequences, KOH and then calcium oxide, so we can just go ahead and erase those guys. And out we get is the 1,3, or in this case, the 1,5 diphenyl pyridine. Okay, cool. All right. Again, let's say that I didn't do these, then we would just have the esters here. No questions asked. We would just have the esters there. Yeah, cool. If I used, let's say I only did the first step and I had an amine, right, dihydropyridine. Cool. All right. B, we have a carbonate. We have CPC here, and we have a serine that's Bach protected. Right, this is the Bach group on the nitrogen. If I think about what groups I have left, I have the carboxylic acid and alcohol. You might be very tempted to do this because you think, oh, amino acid protecting group. But remember, right, the alcohol is much more better nucleophile than a carboxylic acid. So in fact, what we'll get is initially a CPC on the oxygen there as such. And then our second step, HCl and heat, right? That will for sure deprotect our Bach group, right? Bach is sensitive to acid. So we'll get a decarboxylation event on there. Recall that for this group, right, we lose the terbutyl group as isobutene, right? We'll lose the carbamic acid eventually as CO2, And then what we'll get out is the NH2. Now, here's where you have to kind of be clever, right, to get the full answer to this. But remember, nitrogen is a very good nucleophile, and we do have a carbonate here. Okay. I guess this question could have been, this is a bit of a difficult one. I guess you wouldn't have known to do this, but actually this nitrogen will then attack right to give us this. Okay. And then, when the O- comes down, of all the groups to kick off, right, there's 2 oxygens that are very good leaving groups. Probably definitely lose this one because we want to preserve the ring. Okay. So we end up with this product here. So this is actually maybe not the best question because you guys aren't very comfortable with carbonate groups, and actually some of you might have been misled into thinking that they're not very reactive because of that one midterm question. So I guess a better way of asking this would be to get rid of the oxygen here, so that it's just an acyl halide, and then it's much more easier to see what's going on. But actually, if anything, this would be an acyl transfer if we got rid of that, this part here, right? And it would just be an acyl transfer. We're now adding on that group onto the nitrogen. Okay, so this is the much more fair question, I think, right? You deprotect it, and in the heat, right, this can go ahead and cyclize, right, form an amide. So it looks like this is actually a real problem. I got this from an amino acid review where they were talking about how on serines, this is a very common problem. You try to protect the serine, and all of a sudden the amine just jumps in and steals the group, right? So it deprotects the alcohol there. But usually these reactions are run very high excess, so that if this were to indeed happen, then it will get protected again anyways. But I guess in a sense it's kind of clever, right? It kind of supports itself in protection. Okay, cool. All right. So for this question, again, this would be the answer, but hopefully you guys understand how this would work, right? Acylation on the alcohol, and then once you heat this up and hydrolyze off that Bach group, right, the amine can go ahead and snatch that acyl group from the ester and form an amide instead. Cool. All right, moving on. E, we have an aldehyde, or we have sugar, we have a tetrose. First step is zinc sulfur. So we know we're making this here. And so usually when we do this, right, the point of it is to kind of take off this proton. But this anion here is very basic. It would just be quenched by these alcohols. So it's not very useful to make an anion here. But what we could do is hydrogenate this position so that we get a CH3. Right? That's totally possible. Right? Alcohols are not going to really mess there. And then we can do that primary alcohol oxidation. So we get this carboxylic acid here, this dihydroxycarboxylic acid. Cool. All right, moving on. We have a pyridine, Br2. I'm not sure what you guys really saw here, so I just kind of threw what I saw in the textbook. But we'll go ahead and put a Br here, right? Installing the Br there on that 3 position, because that's where electrophiles will go. Very tough reaction, but can get it to work eventually. Mg into CO2, that's an oldie. That makes essentially the Grignard, and CO2 makes the carboxylic acid. So we can do a carboxylic acid synthesis here. NH3 in heat will give us the primary amide. And this here is nicotine. That's nicotine. Cool. Now you guys have to make it. Now, remember that one question we did earlier where we did that Hoffman rearrangement, right? If I do Hoffman rearrangement here, notice what that product is. So actually, let's do this. So let's say I dBr2OH minus. Look at this product. Why might that product be special? Because remember, when I normally do Chichibabin, right, Chichibabin installs 2 aminopyridines. right? So you kind of never really had a chance to make a 2 or a 4. Now remember, the 4 you can kind of solve by, I mean, it's not really solving, but you would have to have a chlorine here, and then you can make the 4 amino pyridine if you wanted to. Okay, but let's say that I had the 3 amino pyridine, or sorry, the 3 chloropyridine, right? If I did NH2 minus here, do you guys think that this would work? Think about that for a second. Do you guys think that a 3 amino, or sorry, 3 chloropyridine will do NAS like it does in the 2 and it does in the 4? So if I have like a chlorine here, right, we know that this will work, right? Without a doubt, we know this will work. But what if I had a chlorine here, or I'll put it here, right? Is that chlorine going to substitute very easily? Again, the reason why the 2 and the 4 are so activated is because they're in conjugation, right, with the nitrogen, right? If we think about sort of like imine reactivity or conjugated imine reactivity. This position here is relatively electron rich. So nucleophiles are going to always avoid this position, even if you have a chlorine there. So in fact, if I have a chlorine at the position, very, very difficult to get an amine to add, or to get a nucleophile to add in there. In fact, if this were to work, right, if not by SNAR, it would have to go by benzyne. In that case, it's always going to be the benzyne would look probably like this. And so in this class, remember, benzyne is to have a very, very hard time, right, controlling that regioselectivity. So if we do get a reaction on the 3 chloropyridine, we'll get a benzyne, very, very bad. I mean, this could be a great explanation question, actually, right? Why is it that we see a mixture of products for the 3 chloropyridine, but not for the 2 and the 4? It's because we have clear conjugation, right? NAS type conjugation in the 2 and the 4. We don't have that in the 3, so the 3 has to go through benzyne. We get a mixture of products. Okay, cool. So what's the solution? The solution is to take your 3 chloro or your 3 bromo, right? Install primary amide via, Mg carbon dioxide, and then, ammonia and heat to get to the primary amide, and then Hoffman to get that 3 amino pyridine. Okay? And so now, right, remember 3 amino pyridine, you can do ortho and para. Usually, very, very quite often, it'll go para. And so now we have some advanced level of direction here. Okay, so just things to think about synthetically, right? How to add all the reactions up to make a very cool novel. Not really novel, right? These are known, but just to make some very cool molecules. Okay, cool. All right. Moving on. G, we have, looks like an amino alcohol. First step, mild acid heat and formaldehyde. So we know that formaldehyde, where that's going to go, it's going to go on the nitrogen. Okay. And so I drew this very suggestively, but once I draw like this, maybe you guys will see it. So I'm going to call this a benzyl group. Okay, but do you guys see what's going on here? Right? Do you guys maybe see a molecule or a type of structure, a motif? I see a 1, 2, 3, 4, 5 diene, a 1,5 diene. This is a cope rearrangement, right? That's what the heat is for. Okay, so remember, cope is just a 1,5 diene, right? There's no other requirement for it, right? It could be any atoms involved. This is sort of like an azeotrope if you think about it, right? Because there's a nitrogen involved. But recall that the cope, very, very easy to draw the mirror of it, right? The way that I do it, if you have trouble with it, is the vertical bond you get rid of, put it in the back. So you reflect it over, and then the 2 pi bonds move away from that bond. So like that, move forward. And then we can go ahead and add everything in. Okay, so we'll get this here. And so what we end up with is an aminium and an enol. You guys recall any reaction that involves an aminium and an enol? You guys said manic. I'm very happy. This is actually what we call a cope-manic or azeotrope-manic tandem reaction. So the first thing that happens is a cope reaction, right? And then after the cope, we have an enol that can attack on the aminium, right, in a manic fashion. So 1, 2, 3, 4, 5. We get a 5-membered ring here in which the nitrogen is involved. Okay, so 1. Well, this needs to be 3. So 4, 5, and then 1, 2, 2. So on 1, we're going to have an aldehyde falling off, right? 2, nothing. 3 has a benzyl group on the amine. 4 and 5 have nothing. If they had something, we would just add them in. Okay. So pretty cool reaction if you ask me. All right. Now, last step, H2PD just gets rid of the benzyl group. Okay. And what we get out is this manic product, this beta amino carbonyl. Cool. All right. Cool reaction. NABH3CN, that should signal to you to a red AM. So that means amine plus some carbonyl, like ketone or aldehyde. I see the amine, I see the ketone, so I know that I'm forming a bond here. 1, 2, 3, 4, 5, and 6. So I'm forming a 6-membered ring here. I'm actually going to move the nitrogen here just to make things a little bit easier, as you'll see. So this was 1, 2, 3, 4, 5, 6. Right, 1 attacked 2, that's where the carbonyl was. 2 had a phenyl ring coming out of it. Right, 3 has nothing, 4 is an oxygen actually. 5 has a carbonyl, and then 6 has a methyl here. Okay, so this is our current product here, right? This sort of aminolactone. Okay, we have a hydrolysis sequence, so that means that we're going to go ahead and hydrolyze on the ester end. And what we end up with is following. There we go. So we have this sort of interesting, weirdly prepped molecule. I forgot why it did this one. I think I might have seen it at that amino acid review and I thought it looked cool. But all the reactions, right? Just know your old reactions. All right. Just so it doesn't confuse anyone, that is a bond, just really short. Cool. All right. Moving on. We have an indole, which again, we talked about indole activated towards that C3 attack. It's just Bach protected. We have, looks like Lewis acid and an epoxide, so an electrophile. Remember, EAS have in C3. So we know that going to add, right, 2 carbons and an alcohol, or the epoxide on C3. Okay. PCC is going to oxidize that into an aldehyde. Okay. And then KCN, NH3HCl, then acidic hydrolysis, what I should have drawn on that first exam. So this is going to be a Strecker synthesis. So that involves getting rid of the aldehyde. I don't know why it keeps erasing. But if there's an aldehyde here, right, we will replace that with COH and NH3 plus. Okay. Acidic hydrolysis also gets rid of the Bach group. Here. Okay. This is tryptophan. Yeah, tryptophan. As you can see, these indole bases are very involved in psychedelics. So if any of you are interested in that, you know, a good book to read if you're interested is Pickle or Tickle. Pretty sure there's 2 of them. I believe Pickle is psychedelics I have known and loved, and then Tickle is tryptamines. I don't remember what the T stands for, but I know what the Pickle is. It's like, it's psychedelics I have known and loved. Very good book. It's written like an org syn prep, so it's very like, you know, specific procedures. It looks like someone's lab notebook. All right, last reaction. Oh my God, last PTP of the quarter. I'm almost getting a little sad, but it's okay. Last one, we have acid, heat, and alcohol. Remember, this is an amino acid, goes selectively on the carboxylic acid. So we make this here. Okay. And then we have MEONA in heat. Okay. Now, a lot of people actually want to, when I've asked them this or talk to me about this, all kind of gravitated towards this hydrogen here. I can understand why you guys did. I guess, an oversight on my part. I should have made sure that it was, not a problem. But what I wanted you guys to recognize here is that we're using OR minus on an ester. And usually when we do OR minus on an ester, right, it's to deprotonate on the alpha position, right? So the protonation is meant to be here, like that. So we form the ester enolate. Okay. And so when you do that, hopefully what you notice is this actually inadvertently forms. This here is an alo ether. This here is a vinyl ether. This is an alo vinyl ether. This is Claisen. Right? This is a Claisen rearrangement. So if I start to redraw this, right, so that everything is in place, I'll just put R here for the, N here, and what's the CBZ group, right? So we'll put that there. Oops, sorry, lost a methyl there. Okay, we can go ahead and do our low refraction trick. Again, or I guess if I wanted, I could do it here. It's easier to do it from here. Right, but what I could do here and get rid of that vertical bond. Right, goes over here, and then the pi bonds move away from it. So I get to here. Go ahead and add everything in. So this would be O minus, and then we'd have a CPCN here. Right, we would end up with this molecule here, which if I kind of redraw it, just looks like this. Okay, H2PD gets rid of the CBZ. It also gets rid of the alkene. Okay, so fancy way of making a leucine. One gripe I have with the biologists, right? Why call this leucine? This looks like isoleucine, doesn't it? Because it has the B, the Y tail you expect from an iso group. So you see this and you think isoleucine, but in fact, isoleucine is this. Isoleucine is this here, which that's nuts, right? Why is this isoleucine? That should be leucine, and this should be isoleucine. So bad biologists, right? Come on, man, you guys had one job. You guys literally had one job. Couldn't even figure that out. Right? Boo, we hate biologists. No, we don't hate biologists, but that is a weird choice. All right, so there we go. That's all the PTP for the quarter. That makes me a little sad. It is what it is, right? Cool. All right, mechanism. I'm very inclined to just skip this because it's in your notes, so I will do that. This is in your notes. Generally, though, amine will attack. Right, so we'll get something like this. Yeah, something like this. Oh, wait, no. I believe it's this first, right? Oh, wait, no, it's this first, yeah. So amine will add in, right? And then this amine will go ahead and attack here. Which kind of sets up the ring. Right, I'm just doing this very fast. That's essentially what it does. Okay, so that's all that is to Edmonds. Not too bad. Okay. This one here, this might look a little weird, but if you think about it, right, it's just diazotization. We form the N2. If you kind of look at it, hopefully you can see what's going on, right? The N2 like pi bond is still preserved, so you can tell that this is clearly the N2. Right? And then the aniline is just attacking the nitrogen. It's like doing kind of like a diazo coupling type thing. Before I get any nerds that say that this is just completely me making this up, I do have source material on this. I made sure this works before I wrote it. But this makes a triazole. Okay, so nerds back off. I have the literature. Okay, I have the literature. Oh, my bad. I should not have drawn it like that. My bad. But I have the literature. Okay, I know it works. Okay, cool. All right. This one might have been a little trippy, but again, if you kind of look at it, 1, 2, 3, 4, 5, 1,5-dicarbonyl. This is going to initially be a cope. So this would be like an azocope or a diazocope because there's two of these amines here. Actually, if you really want to think about an analog for this, right, the best one is probably Claisen. So this is like a Claisen condensation, or sorry, a Claisen rearrangement with with a phenol, where this would go to, like initially what it'll do is it'll do this. Right, where it goes from here to here. So if you want to kind of copy that idea, that's essentially what's going on. Yeah, like that. Okay, and recall that this tautomerizes almost instantly to restore aromaticity. Okay, yeah, so it tautomerizes almost instantly to restore aromaticity. Same thing will happen here. And then from here, it's just Paul Nor. Right, remember Paul Nor, just attack there. And eventually, right, I mean, to mild acid, so you could protonate this if you wanted to. Right, you'll just lose out ammonium. Right, get out the indole. Okay, so like an azoclason is what I would call this. Azoclason into Paul Nor is essentially the idea here. So very, very cool reaction if you ask me. Cool. All right. You can even see here actually that this was a 1,4-dicarbonyl. Actually, would it look like this? 1, 2, 3, 4. So that's also your giveaway. That's a Paul Nor. It's a 1,4. Cool. All right. Syntheses. So these are a little bit harder, just to make you think a little more, but nothing too crazy. These are just like two more ideas I have for possible syntheses. So this one here, we start with an aldehyde, and if we look here, we end with this complex product. But if I look, I have a free amine, and I have this carboxylic acid, NCC, NCC. I have a dipeptide here. Okay, so this is my peptide bond. Okay, so we're going to be doing definitely some DCC chemistry here. Now remember, the peptide bond is the point of the DCC coupling. So this here, this amide bond, right? I'm making that with DCC. Okay? But recall that when we do this usually, our free amino and free carboxylic acid groups are usually protected. So we're probably doing some deprotections here. So I'll put here PG deprotections, just kind of blanket term for all of them just for now. Okay, but I'm definitely adding in some PGs. I'll just put P for protecting group. I definitely have protecting groups on. Right, on these free groups here. And that's just to prevent them from reacting in the DCC step, right? So for sure, we have these here. So we'll have DCC, right? That's just forming this bond here. So I can go ahead and lyse that. Okay, so I can get these two pieces here. Okay, so again, we're cutting right there. Okay. All right. Now, in order to figure out which amino acid we started from, just look at the R group, or I mean, this is an aldehyde, right? So clearly we're doing Strecker. So you could just go ahead and do a Strecker, which I will just on the side do very quickly. Yeah, and so you can see clearly where we start from, right? We're going to go ahead and make this the valine, right? Instead of the aspartic acid. Okay, we can just throw in the aspartic acid with the DCC. Okay, cool. Now the protecting group will really be up to you. I would recommend trying to do some kind of orthogonal protecting group. So for example, if you choose to do a Bach, so one really quick way to write Bach is like that. or at least the installation of it, right? If we do Bach, then we can use methyl esters here, okay? And we can essentially hydrolyze an acid. So we can do acid hydrolysis here to get rid of the methyl esters and also get rid of the Bach, right? The methyl esters are a little sketchy because they are they're esters, sorry. So they are a bit, much more resilient than like a Bach group. But, esters are much more easy to break than amide. So I wouldn't worry about your amide degrading in a process like this, right? Like I wouldn't be afraid of that. Okay, so this is one way to do this orthogonally. Or sorry, not orthogonally is what I meant, sorry. So this is the way to do it so that everything is congruent, right? Orthogonal would not be congruent, so I apologize for using that. Another way you could do this is to just CBZ everything. It's probably the safest option. But if you have CBZ on everything, right, then you can just do H2PD, right? Hydrogenation will get rid of all those protecting groups. So cool. So when you're doing a dipeptide synthesis, don't be afraid of it at all, right? Just look for your peptide bond, recognize that every free group has to be protected, and just move backwards. You always get these correct. Okay. In this case, we just use Strecker just because, right? But maybe, like if we had started from like here, maybe we do like oxidation and then right HVC into the amine, and then maybe protect, blah blah blah, all the shenanigans, whatever you have to do. Okay, cool. All right. So just to get your brain juices flowing on that kind of synthesis. Here we have, looks like a heterocyclosynthesis. Again, looks very crazy, but it's not too bad. Okay. Pyridine is retained, but we do add a pyrrole. Remember, pyrroles, any 5-member rings, cut on that heteroatom bond. Yeah. So what we'll release is the amine, and also this here, right, which will just be a 1,4-bicarbonyl, just like that. Right, just like that. So just throw in some heat, condense that will turn into a pyrrole very, very easily, no doubt about it. And again, the question becomes, how in the world do we functionalize the C2 position to have this CH2 NH2? Hopefully you guys recognize what this fragment is from, though. So maybe actually see an answer to that question. Where does CH2 NH2s come from? Those come from the reduction of nitriles, right? That's a very common fragment. So you can, technically you should be using H2PD here. Actually, okay, both these kind of suck. Especially lithium anhydride. That could definitely hit into the pyridine, but you guys didn't learn that, so it's okay. So either one of these two, just use them. But you could for sure, get that from a nitrile. Question is, again, how do we functionalize the C2 position to have a nucleophilic component that is not Chichibabin, right? The Chichibabin amine, right? Because that's the only thing that can reliably add there, right? If you kind of force it to do so. So again, what do we use, right? We use the world's best leaving group, which is the N2+. So we use HONO with CuCN, NaCN, right? Gives us the cyanide, which we can very cautiously hydrogenate or very cautiously reduce with the hydride, get our ethylamine arm, or I guess methoxy, or not methoxy, what would you even call this? Like methamine? Whatever. Anyways, you get your amine arm, which you can then turn to a pyrrole. Okay. I guess an alternative pathway you could take to avoid this problem, you could, obviously you guys don't care about this, probably won't, but it's okay, is to go through the aldehyde. So dibble this, go through the aldehyde, and then do reductive amination. Yeah, you can probably do that and then do that. This adds a step, but it prevents you to have to worry about, this is like a practical thing. This will prevent you to have to worry about doing any unnecessary reduction on the pyridine. Cool. All right. So again, just getting you guys to think about how to functionalize these odd positions, right? Because that's really what we want to care about. or I mean, that's really how we can fold in previous material. And then recalling how we talked about how we could install an NH2 here, that would be interesting to install an NH2 there and then add like a pyridine. That'd be pretty interesting, right? Or sorry, a pyrrole is what I meant to say. That'd be a really interesting linker molecule, right? You can imagine this is not a very activated pyridine, right? Why is this not? I mean, that's actually a really good question, right? Why is this pyridine not as activated as, say, like the free aniline version? Right? That could be a good, explanation question. It's because this lone pair will easily delocalize into the system, but this lone pair, right, wants to stay in its aromatic system. It doesn't want to go and enter another system. So not a very activated pyridine this one is, because that pyrrole N wants to stay as a pyrrole N, right? It doesn't want to join the pyridine party. Cool. All right. So, oh my God, that was the last synthesis. Actually, when I first wrote this problem, I had a different idea in mind. I drew a loaded fucking pyridine, but it was it. I think I put like an NO2 here. I put like a methyl here. Yeah, I did some like crazy crap like this initially. Because what I wanted to do was get you guys to do this. And then what did I want to do here? Shit, I can't even remember. I wanted to do something stupid. Oh, so I wanted to get to here. Oh, I remember now. I wanted to get to here. So the diazonium into nitrile into reduction. So a lot of steps. So you can see why I think what I wanted to actually do was start from here, just to reduce the number of steps. So it's already at 3 now, but you can get this down to N2 plus again. Oh no, so I wanted to do, I remember now. I wanted to do this, right? Turn it into this guy here. And then, so like maybe a methyl here or something, right? Turn this into NH2, right? And then turn that NH2 into N2 plus. And I was trying to look for literature where it would prove that you can get that attack there so that you could make a really weird molecule. Right, 1, 2, 3, 4, 5. So like that. Yeah, I wanted to do this, but I couldn't find any literature on this. Apparently, it just doesn't exist, or I'm just really bad at using Reaxis. I don't know. But how cool would that would have been, seeing something like that, right? I imagine a lot of you. I mean, the cool thing about this is if I start from here, you've been given so many of the pieces, like it's basically handed to you, right? Like you can see, I mean, if you just kind of think about breaking this up, right, you can see that the pyridine nucleophilic portion, or sorry, the pyrrole nucleophilic portion made a bond with the NO2, so clearly we turned it to an electrophile, so the N2 electrophile. So you can easily trace back to here. From there, we can trace back to having the NO2 here, and then cut here and here to get to the, this here, and then, obviously blah, 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 whatever. But just, my own little, I mean, obviously you can see this is a long one. It's not very easy. You can't just do it instantly. And usually the rule of thumb is like 5 steps for these syntheses. So, but cool stuff, right? Cool stuff to think about. Whatever. Anyways, so last synthesis of the year. Definitely a nice one to end off on. I'm happy with it. Cool. All right, explanations. So scientists at Gymnasia Pharmaceuticals found that their methyl ester alhistidine would racemize during attempts to protect the amino group, right, and predict why it is racemizing. So probably the best way to approach this is to think about what could potentially be attacking at this position here. So this is the alpha position of an ester. And recall that alpha position of esters have hydrogen that is particularly acidic. So it's very likely that this proton is what's being taken away. Now, it's not as simple as saying that O- is going to take this proton, because if that were the case, then the amino acid identity should not have mattered. So I imagine a lot of you might instantly do this. Not a bad idea. right? Definitely, if I was grading the exam, this would give like 4 out of 5 of the points, right? Maybe, yeah, I was gonna say 3, but 3 is a little mean. 4 out of 5 for sure you would get if you did that. But really, the important thing here is that it's histidine, right? It's histidine that's doing this. So is there maybe another proton that's more acidic that could possibly be being deprotonated? Oh, there is a pyrrole. And so what's going on here is that the imidazole pyrrole end is getting deprotonated, right? Electrons are swinging over here, and it's these electrons that grab the hydrogen. Okay, so keep in mind here, right? It's important that the identity is taken into account here, right? Because that's really what's facilitating this isomerization. Okay, and so now, right? I mean, it's an epimerization if you think about it, right? Either we add the H back in the same spot or it goes to a different spot, right? That's how we're getting the racemization. So this just goes ahead and grabs that proton again. Swing out, this goes ahead and grabs a proton, right? Probably from the methanol. So that's the mechanism of this, not too crazy. Just keep in mind that if we give you a component, a specific amino acid component, you better use all of it, right? Because that's the whole point. That's the reason that's what's conducting this polymerization. This polymerization is a huge problem, racemization of that center. Because remember, amino acid is very specific. If scientists is trying to make an amino acid, they want it to be perfect pure, right? They want it to be exactly the center they want. And so for this fact, imidazoles are usually protected. This amines hydrogen, this pyrrole hydrogen, usually always switched out with some kind of group. Because again, you don't want this facilitation of racemization. Otherwise, you've destroyed your stereocenters. You destroyed the activity of whatever you're making with this histidine. Okay, cool. All right, that's the first one. Scientists also tried this, where they tried to do, looks like this NAS here. Okay, we talked about this. Pyrroles are already very electron rich, right? They got a lot of pi juice. They don't need any more, right? They're already drinking the Kool-Aid. So issue here is that, right, these guys are built to do EAS, and yet my scientists were trying to do NAS, so shame on them. But we talked about this. How can we solve this? What do we add, right? We just add an EWG. So we could do a fatal crafts, add this in here, and now this will work perfectly fine, right? Because the electrons can sink into the ketone, and they can come back down, kick out the bromine, and we get our, well, initially it'll be this, right? But after the hydrolysis and decarb, it'll be the acid. Now, if you specifically use this group here, right, it's done on purpose, this phenylketone, you actually make the drug ketorolac, just an NSAID. I don't know if they still use it, but it's an NSAID. So it's used for NSAID things. Yeah, cool. All right. So those are two explanation questions. I can see how these might have been difficult. I could see that. But again, it's all about if I push you guys, then when you take the exam, which is inevitably going to be easier, because the exams never seem to push you guys, then you'll do very well at them. Yeah, cool. All right. Although both contain nitrogen atoms, blank is electron poor, so this is pyridine, this is pyrrole. Blank involve interaction between protein R groups. So protein R groups interaction, that's tertiary structure. Bunch of things can be this, salt bridge interactions, pi stacking, hydrophobic, hydrogen bonds, disulfide bridges, a lot of things can fit here. So just choose your 3 favorite. Okay. Oh, I wrote the same question twice. I'm actually an idiot. Amino acids exist as charged. Generally, amino acids with COH are acidic, right? Because that's an acidic group, and they have low PIs. The heck? Oh, sorry. I got a text. It's like 3 a.m. and I got a text. That was kind of weird. Anyways, moving on. Protonation state. You can do the trick really quickly. So just treat the pKa's as the midpoints. or as like neutral points, and then just plot. It's as easy as that. So we have pH of 3, 3 is here, 3 is here, and 3 is here. So I just want to draw this very quickly. This is going to be O minus. This is going to be NH3 plus. And this is going to be NH3 plus. Okay. 7.4, 7 is here. 7 is here. 7 is here. Right, so we will have the oh, did I? I guess this is kind of useless. This didn't really help, or it didn't really change anything. It's the same. So I should have chose a better. My bad. Oh no! Oh my god! It's not 10. It's not actually 10. It's like 14. My bad. Shoot. Okay, whatever. It's okay. It's okay. It's okay. No big deal. That's the only one I messed up. It's like 14. But that doesn't change anything though. Oh well. 14, that's all over here. So NH2, NH2, and then O minus. Okay. That is just the form there. Cool. All right. Now, again, for the PI, just quickly see if I accidentally made the positive. I did not. I did not. Or sorry, the neutral. So that's +2. Oh, wait, no, that's +1, right? This is +1 because I fucked that up. And this is -1. So boohoo, did not do it. So in this case, I can use that little trick that I talked about where you just make the most acidic form. And then just kind of move up until you get to the neutral form. So the first pKa is 2.2. Okay. 2.2 is associated with the carboxylic acid, so it goes from OH to O minus. Okay, that's not neutral, so we've got to keep going up. Oh, actually, we don't actually keep needing to move up because, well, if this is not the PI number, then obviously, right, this form can't work. Obviously, this form can't work because that's also not it. So that would leave us with this and this. The only one between two pKa's is this and this, right? So that this would be neutral. Right, probably through this form here. So look at that, just using deduction. I don't even have to think about chemistry, just use deduction. Let me get this right. So it should be like 14 and 9.1, which, shoot, 14, 9.1. Just do the math. It's the whatever's in between those two. That's like 23, right? 23 divided by 2 is like 12.5, something like that ish. My bad. But yeah, cool. All right. So again, this should take you guys no more than 5 minutes to do on the exam. It'll be fine. Cool. All right. Circle the most acidic molecule. Again, acidity, just going back to the whole idea of pyridines are electron poor, pyrrols are electron rich. So clearly it's between these two pyridines here, right? These guys are off the table because this is like an NO2, right? Okay. We have an EDG here, and we have no DG, just the EWG. That is the pyridine N. So this guy's going to be the most acidic. All right, so secondary structure. So remember that amino acids, or sorry, proteins have 4 different types of structure. Very quite often people like to go from primary and move all the way up. I like to think about it backwards. I think it makes the most sense to me. Like if you were to look at a protein, right, just from the highest possible view, a protein is the interaction of many polypeptide chains together. So for example, hemoglobin, right? Hemoglobin is, it looks like a tetramer, but it's actually 2 dimers, right? It's an alpha, beta, right? And so the interaction between multiple protein polypeptides, right, is what quaternary structure is, right? This is the first thing you see, okay? When you look at a protein. So that's quaternary structure. If I took one of these, monomers, like for example, the alpha monomer, right, and I were to zoom into it just a little bit, just so I could see what interactions are holding it up together, what I might notice are polypeptide chains, like millions of these guys, that are being held in particular ways by R group interactions. So for example, I might have like an aspartic acid that is holding a certain chain via a salt bridge with like a lysine, for example. So this salt bridge could be holding these two chains in a particular way, very specific way, in order to induce function. I might notice that there is a tight, cavity here, and that's because there are two cysteines linking opposite to each other to make a disulfide bridge, make a cysteine. Okay, again, R group interaction. I might notice that in this pocket particular, like if this is aqueous, inside here is all the hydrophobics, right? So all the like hydrophobic stuff is in here, stuff like that. I might notice that maybe in this pocket, there's like a pi stacking interaction, right? I have two aromatic rings that are perpendicular to each other, right? And it's their pi stacking that's kind of pulling this ring at a certain distance from each other. Whatever you can think of in terms of R group interactions, that's your tertiary structure. That would be the first thing you would see when you take that monomer and you zoom in a little more, okay? If I were to zoom in a little bit more into the structure to see what these, individual structures, how they might be oriented, I might notice that amino acids are, held in sheets where the backbones, right, the backbone amides are forming H bonds to hold these structures together. So one thing is you can make is a beta pleated sheet. And again, that's just a bunch of these backbone amides, holding each other, right? So it's the backbone H bonds, right? This would be R group interactions, right? Alpha helices, great example of this, right? Right, so you would have this here. You have this here, right? That's being held together. Cool thing about alpha helices you'll learn in Biz 102 or whatever biz you take. There's certain amino acids that can exist here at the kinks or at these turns, and certain that can't. The Rama-Chandran plot plays a big role in this because of degrees of freedom every amino acid has. So cool stuff there. To be honest, I knew this stuff really well when I took a Biz 102, but now it's like whatever to me because I haven't really touched this stuff in a long time. So I apologize if a lot of things I'm saying just like kind of crap. But anyways, this is our secondary structure. And if I look in just a little more, if I zoom in just a little more to see what's actually building up these structures, what I might see or what I will see are a bunch of amino acids, right? So amino acids that are linked together by these amides. So the peptide bond is the primary structure, right? It is the actual peptide bond that is making up these, or that's holding up these amino acids together. Okay, so for the most part, you guys kind of learn this from the bottom up, and I think that's fine. I just personally find it easier to think about it, and I like presenting it from the backwards perspective, right? You start far out and you go in to see what do you keep seeing as you go down, 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 right? Quaternary being the most overhead structure to all the way down to the primary. What is the primary thing that is holding together these proteins? So fundamentally, it is these peptide bonds, right? And then these peptide bonds, right, can form these intermolecular H bonds that can make these beta pleated sheets, these alpha helices. And then if I look out a little more, right, what else can hold these sheets together? Like what can hold various sheets or various alpha helices close to each other? It's these R group interactions that can hold together. And then it's these millions of R group interactions between different polypeptide chains, right? So like in the alpha and the beta unit, right? One dimer of hemoglobin, right? So millions of these interactions between them that can bring together two polypeptides to cause a enzymatic function. So pretty cool, right? Cool. All right. So with that being said, secondary structure is amide H bonding. So we need to be able to have H bonding. That's this first one here. right? This can H bond. Oops, sorry. Right, that can H bond. So that's this one here. This would be an ionic interaction. So they're tertiary structure like. This only has a peptide bond. So it, I mean, well, that doesn't really make it a primary structure, but I guess characteristic like that. Yeah, cool. Sorry. All right, most aromatic heterocycle. So all you have to understand for aromatic heterocycle is just the series that was presented in class. Of the heterocycles you guys learned, pyridine is the most aromatic of those heterocycles, followed up by thiophene, followed up by pyrrole, followed up by furan. Now, I imagine a lot of you are going to try to, associate some kind of trend to this. And I'm going to tell you right now, don't. There is no good trend that can explain all of this, why certain things are more aromatic than others. All you really need to know is that aromaticity, very broad subject. I mean, people spend years on this. There's whole textbooks on what aromaticity means and what it isn't. And so many things go into, I mean, people have tried to quantify aromaticity and try to find some way of determining it. The reality is very hard to point at one or two things and say that's what's making something aromatic, or that's like that is what defines aromaticity in each of these problems. It's better to just take our word for it that these structures colloquially, right? I mean, these are just the structures, how they align against themselves, right? One way you can kind of rationalize it is that these two guys here, the ones that are most like benzene, are just not very reactive, right? They're less reactive than normal. Like again, this is a nitrobenzene essentially, so very, very unreactive. So that's why it's very close to benzene. Same thing with thiophene, right? Thiophene doesn't have very good overlap with the cyclopentadienes ring, so it's not very reactive. But I mean, furan is less reactive than pyrrole. Pyrrole is way more reactive. Like if we're looking at reactivity series, pyrrole is insanely more reactive than furan, and yet furan is less aromatic, right? So again, very, very hard to boil down some trend or some rule or some law. It's just better to just remember this. Write it on a note card, right? Write this on the note card, but this is the trend for this, okay? So yeah, I mean, looking at this, this is the thiophene, so just get rid of all that, right? I mean, I know that there are those ends in there, that was just to kind of like fuck with you guys, but it's the thiophene. Okay. And that's crazy too. It's like you insert a pyridine end into the thiophene, and the thiophene is still more aromatic than the furan. So, wild. Cool. All right. So at least the NMR, we'll do this one. So this is the matching. Let me try this out because I can see how this was a little difficult to look at. Oh, I see what I did. I used the, okay. I blocked a lysine. Okay. Oh, I blocked and I estered the, okay, cool. All right. So going through this, right, again, you don't need the multiplicity. I imagine a lot of you were not happy that I didn't put it in. You don't really need it, to be honest. You just have to use, you can really just use electronegativity and, de-shielding theory to kind of get through most of this. You can see a bunch of broad peaks in here. Remember, broad peaks associate with protons that are like NH2s or OHs. So I definitely believe, I mean, at least this one up in 9, that's got to be like some kind of like OH or NH. There's two of these guys here, right? There's an NH2 and there's an NH. This NH2 or this NH is, right next to, I mean, it's in the mid. So you can imagine it's very acidic, whereas this is just an amine, right? Recall that acidity increases with hybridization. So this anion, if I were to protonate this, right, would resonate. This one wouldn't. So I'm willing to believe that this proton here, which would be G, is going to be this guy here. And then this one here, which would be B, is going to be this guy here. Okay, so those broad peaks that are associated with NHs, right? Just going with, who would be more de-shielded, right? We have one that's right next to a carbonyl, one that's one away from a carbonyl. That's another way to think about it too, actually. How close they are to other electronegative units. Cool. So we got those guys out of the way. All right. I see here, it looks like a bunch of protons from 7 to 8. They all clump into 1, so they might all just be the same. If I kind of look here, 7 to 8, that's usually aromatic. I have an aromatic ring. I think it's these guys, 3 guys here. Should be I, J, and K. It's actually marked on here. So I, J, and K. Right, got those guys right out of the way. Cool. I have a proton up at 5 and a proton at 4, right? Recall that between 3 and 4 is usually where you have protons next to N or O, right? If they're above 4, like at 5, they're usually next to N or O and something else electronegative. So when I look for these positions that are next to N or O, that would be here, 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 and here, right? So those are all next to N or O, right? Let's focus on the O ones first, because the O ones are probably the most issue. It's probably these two here. We'll focus on those two first, right? We have a CH3 that's just, right next to O. We have a CH2 that's next to O and a benzene ring. Okay? Because this is next to two deschooling options, right? A benzene ring, so an sp2 center and oxygen, I'm willing to bet that this H or HH is right here, and then A is right here. Okay, cool. So that would just leave then this proton and this one here. Sorry, this one here. So HI and HC, which are next to the N. Actually, these are a little. Yeah, actually, this is a little hard to tell. I mean, yeah, they're both triplets, so you actually can't really tell which one is which. So I think that's why I put these two boxes next to each other. Yeah. So C and L, right? You wouldn't be able to tell. All it leaves is D, E, and F, which actually also these can't you tell. You can't tell with these either, actually. I think about it. So these could be any actually. Okay. Cool. All right. You can't tell because there's nothing electronegative that can push you to believe one would be. Oh, actually, okay. Well, actually, E is the most isolated from. Like it's sandwiched between D and F, which are closer to electronegative things. So in fact, actually, E is clearly this guy. But whether this is a D or F, right? That's kind of, we don't know. Cool. So there you go. That's how we can quickly solve these. With multiplicities, you'll have way more control, right? You can probably figure out more of these, but yeah, again, just use delocalization theory, you'll be fine. All right. Last problem of the quarter, NMR problem. Again, I will just give you the answer here, simply because it's most likely to be a matching. But we could even build this if we wanted to. I mean, I see the twin towers, so. Oh, actually, one little trick here, in case it is a build an amino acid or build a NMR, sorry. Whenever you have these like broad peaks, right? That's kind of like your giveaway to think about, especially when they're all the way up at like 12, 14, or around like 8 to 10. That's like your giveaway that these are like amino acids or some kind of dipeptides. So yeah, so clearly we have something like this here. Okay. Well, my guess is this is a dipeptide. Not that's my guess. I'm pretty sure of this. I'm pretty sure I did this. And I did, oh, I see what I did. Yeah, okay. Cool. And then I'll have this here. Okay. All right, cool. So I have this here. This is the dipeptide tyrosine alanine. Okay. Now I just gotta put protons where they gotta go. So again, this is super easy. That's just that there. So if I call this 1, right, 1 will be right here, right? This is a carboxylic acid. That's not too hard to figure out at all. I have a broad 2H, right? That's also not very hard to figure out. Right, that's just gonna be this guy here. Oh, sorry, this guy here. Right, my broad 2H, so oops, sorry, those 2. Okay, cool. And then I have, oh, okay, so this is a little tricky, right? I have a 1A singlet, a 1A singlet. That's they're broads. It's either this NH here, this OH here. Again, just use de-shielding theory. OH is more electronegative, so this should be 3, which is up here, and this would be 4, just right here. Cool. I have the twin tower 6 to 8, so that's just the pair coupling. You can actually figure out which one is which specifically, right? The one that's more de-shielded should be the ones that are meta. So, sorry, so this would be 5. And the ones that are less deshielded, these guys here. Wait, why am I using different colors? Sorry, I'm losing my mind. Right, it's gonna be these here, right? The ones that are ortho, because EDGs, right, send electron density orthopara. So those are going to be less deshielded. Cool. Now it's just a matter of what are these, atoms next to. So, for example, I have now this here. I have stuff around here. Again, if it's above 5, right, or above 4, usually it's next to 2 electronegative atoms flanked by 2 electronegative things. So, I actually have 2 positions like that. I have a position here like that, and I have a position here like that, right, where this H and this H are both flanked by an acid and an amine. So actually, I guess you could use, you can actually use, this would be a perfect time to look at coupling, right? Coupling will tell you. So this H here will be a quartet because it's next to 3 hydrogens. This H would be a triplet, next to 2 of them. So if I call this 6, if I call this 7, the triplet is 7. Okay. And this is a quartet, so that'd be 8. Okay. That just leaves a 3H doublet, which I'll call 9. It's got to be this. And then 10 is going to be the last 2H, which is this guy here. Okay, cool. So look at that. Just disconnect, or all of that just deshielding theory, right? Electronegative theory. That's all we needed. And with that, we are done. That's it. That's the last exam for the quarter.